Alrighty. I apologize for being a few minutes late. And also I apologize for not having put up the exam three review materials until literally like 5 minutes ago. But they are all up on Canvas now. Again, I'm very sorry that I had forgotten to do that, even despite some of you reminding me. But they are all available now. Um, I'm happy to answer any questions that you guys may have on those problems this weekend while I'm working on your test. We'll also have a review session on Monday, and I will be available to answer questions throughout Tuesday and Wednesday as well. All right, so in today's class meeting, we are going to continue our talks regarding complex power. So let's call this lecture Complex Power Continued. To very briefly recap what we talked about in our last class meeting, we learned about complex power and the relationships regarding the real parts of complex power, imaginary parts, magnitude, angle, all of that kind of good stuff, which was all summarized for us in what I call the power triangle. And I'm drawing one of those here, where the horizontal axis corresponds to the real part of the complex power, and the vertical axis corresponds to the imaginary part of the complex power. So whenever we have some complex power S, its magnitude is referred to as the apparent power. The projection of the complex power onto the real axis gives us our average power. The projection of the complex power onto the imaginary axis is what gives us our reactive power Q. And the angle between the positive real axis and our complex power S is our power factor angle, theta S. So these relationships are summarized mathematically as S is equal to the RMS phasor voltage V multiplied by the complex conjugate of the RMS phasor current I. That is our fundamental relationship for complex power. And then in rectangular form, this becomes average power measured in watts plus JQ, reactive power measured in vars, is equal to apparent power measured in volt amperes with an angle of our power factor angle, theta S. So I tried to encapsulate everything as best I could here pretty quickly. So let's now talk briefly about alternative relationships. Okay. And this is what's going to help us kind of sort out the roles of our different circuit components and how they function in a complex system, okay? So everything that I'm about to do starts with the fundamental basis that complex power is simply the product of RMS phasor voltage times RMS phasor current conjugate. And we're also going to use Ohm's law in the RMS phasor domain. So before we are able to use Ohm's law in the RMS phasor domain, can anybody tell me what Ohm's law looks like in the frequency domain?
Is
Phasor
it
V equals phasor I and impedance.
Exactly right. So in the frequency domain, we have the relationship V is equal to I times Z, right? Well, we're currently in the RMS phasor domain. So let's look at something here really quickly, right? Um, Based on Ohm's law here, we could express our impedance Z as the ratio of phasor voltage V to phasor current I. In fact, that is literally how we defined it when I introduced the concept of impedance. Well, if I have phasor voltage V divided by square root of 2 over phasor current I divided by square root of 2, effectively I've just multiplied my impedance definition by a factor of 1 over the square root of 2 over 1 over the square root of 2, which is just a fancy representation of the number 1. This actually gives me my RMS phasor voltage divided by my RMS phasor current. So impedance can now be thought of as the ratio of phasor voltage to phasor current or RMS phasor voltage to RMS phasor current. And the reason why that works is simply because to go from a phasor voltage or current to an RMS phasor voltage or current, everything just depends on a common factor of square root of 2. Okay. So we're scaling things by the same amount. Our impedance relationship literally does not change. So impedances in the RMS phasor domain are exactly the same as impedances in the frequency domain, like what we've been dealing with for the last several class meetings. So it should be pretty easy for us to see then that in the RMS phasor domain, Ohm's law just looks like RMS phasor voltage V is equal to RMS phasor current I times impedance Z. Once again, Ohm's law is just Ohm's law. That's one of the great things about it is it's always the same. So if we use our definition for complex power and Ohm's law, we can actually express complex power only in terms of RMS phasor voltage or RMS phasor current, meaning that we can calculate complex power knowing less overall information as long as the impedance is known. So this is really just kind of a shortcut for us to do a little bit of our circuit analysis without having to know literally everything that's going on all the time. Okay. So using these relationships, we could say that S is V times I conjugate, and I conjugate could be written as V over Z, and then we conjugate this ratio. Well, when we conjugate a fraction, that's the same thing as performing the complex conjugate operation on the numerator and the denominator. So this simplifies to V conjugate times V over Z conjugate. Now, can anybody tell me what V conjugate times V should be equal to? I believe we discussed this in our complex numbers review, but it's okay if you've forgotten since then.
is it just the real part?
So it is not just the real part, but that's a pretty good guess. Let's look at what happens really quickly here. I'm going to do this in blue, and I'm going to wind up erasing it here in a moment because once we figure out what it is, we'll reinforce it here in a moment. But let's say I have a complex number A, and I'm going to express this complex number in polar form. So we'll have the magnitude of A with an angle of theta A, what would A conjugate be? So does anybody remember what the conjugate operation does for us? Or how to do conjugate operation, I guess would be a better way to phrase that. I'm sorry for interrupting you.
Oh no, doesn't that just change the magnitude?
So it doesn't change the magnitude, it changes the sign on the angle. Okay. So in polar form, the conjugate operation changes theta A to negative theta A. In rectangular form, it just changes the sign on the imaginary part. So A conjugate would look like the magnitude of A with an angle of negative theta A. When I multiply those two things together, that's going to look like the magnitude of A, angle theta A, times the magnitude of A, angle negative theta A. What's that going to give me? So you should be able to test this out in your calculator just by putting in a random magnitude and a random phase angle. Put in something easy like 5 angle 10 degrees and 5 angle negative 10 degrees, and multiply those two together and tell me what you get.
You just get the 5 multiplied by itself, the angle just goes away.
Exactly right. Thank you for that, Haley. So this is literally just going to look like the magnitude of our complex number squared. The phase relationship completely cancels out. And so we effectively get the magnitude squared with an angle of 0. We can just throw that angle of 0 away because it doesn't really help anything, okay? So putting that in the context of what we have above, let me erase this really quickly, tells us that we can compute the complex power absorbed by an impedance if we only know the magnitude of the voltage drop across it and the conjugate of the impedance itself. So we don't even need to know the phase angle of the voltage anymore. Literally just the magnitude squared divided by the conjugate of the impedance gives us our complex power. Okay. Now, that may seem odd that that little amount of information is enough to calculate the complex power, but let's think about things here in context, right? So this is another quick aside just to kind of let you guys understand what's going on under the hood here. But our power factor angle, theta S, was defined as theta V minus theta I. Well, our impedance, Z, is the magnitude of our phasor voltage, our phasor voltage divided by our phasor current, which comes out to be Vm over Im with an angle of theta V minus theta I. So the angle of the impedance is the same thing as the power factor angle, which is why if we know the impedance, we only need to know the magnitude of the voltage. The impedance gives us the rest of the information about the complex power. Okay, so that's a pretty interesting thing. When we talk about power factor here in a little bit, sometimes we can literally get away with computing power factor just by knowing what our impedance is and doing no other analysis whatsoever, which is a pretty handy tool sometimes. All right. So we have that relationship for voltages. Now let's see what happens when we're trying to express everything in terms of a current. So once again, we can start with the relationship that S is equal to V times I conjugate. Now we're going to just directly substitute in Ohm's law. So replacing V will be I times Z. And then we're going to have I conjugate over here. This looks like I conjugate times I times Z. Well, what should I conjugate times I be?
The magnitude of I squared.
Exactly right. So now we just need to know the magnitude of the current, square it, and multiply it by the impedance. And that gives us our complex power. So using this relationship, if we know impedance, we literally only need to know the magnitude of the current in order to calculate our complex power. So these two relationships can be a pretty handy way to calculate complex power, just because they don't require us to know a whole heck of a lot of information. Okay. Let's take these relationships one step further. Okay. What if we had a resistor? Okay. So if we had just a resistor, what would the impedance of the resistor be?
The resistance of the resistor.
Exactly right. What would the conjugate of that impedance be? So what's the conjugate of R angle 0?
R angle 0.
Exactly right. So that means that for a resistor, the complex power is nothing more than the magnitude of the voltage squared over R, or the magnitude of the current squared times R. Effectively, these are the exact same thing as our DC relationships, which should make sense because the effective value of an AC signal is a DC representation of that signal. So let's look at this a little bit here. Is there any imaginary part of this complex power? Is there any J literally anywhere in this thing?
No.
No. So that means that resistors absorb average power. They make no impact whatsoever on the reactive power in a system. All they do is contribute to the real part of the complex power. So resistors are principally related to average power only. If we look at an inductor, what is the impedance of an inductor?
Is it a J omega L?
Exactly right, Baylor. Thank you for that. So in our first relationship, we would have the magnitude of the voltage squared divided by the conjugate of J omega L. Well, the conjugate of J omega L is just negative J omega L. So what does 1 over J equal to again?
Is it a negative or just negative, or I forgot.
Negative J. So 1 over J is the same thing as negative J. So to me, that means that 1 over negative J should come out to be positive J. So this could be written as positive J times the magnitude of the voltage squared divided by omega L. In terms of the current, we would just have J omega L times the magnitude of the current squared. So let's call this J times the magnitude of the current squared times a factor of omega L. Okay. So looking at these inductor relationships, is there any real part?
No.
No. So our inductors are only capable of contributing to the reactive power, which I believe I mentioned in our last class meeting. Now, is it possible for us to ever get a negative number using these relationships?
No, not that I'm aware of.
So even if our current is somehow had a negative magnitude or something like that, because we're squaring it, it's always going to be positive. The inductance value itself will always be positive, and omega, our frequency, will always be positive. So the complex power absorbed by an inductor is really just reactive power, and it's always positive. So we could say that inductors absorb reactive power. So that's what they do in a steady state sinusoidal system. Lastly, we'll look at capacitors. Okay. So what's the impedance of a capacitor?
1 over
One
J.
over J.
So 1 over J omega C. Thank you guys so much. So that's going to look like the magnitude of the voltage. Sorry, I need to put that square symbol outside of the absolute value thing, over 1 over negative J omega C. The negative sign came from the fact that we're doing the complex conjugate. So this is simply negative J times the magnitude of the voltage times omega C. And in terms of current, we are going to have the magnitude of the current squared divided by J omega C. And as we just mentioned a moment ago, 1 over J is the same thing as negative J. So this is going to look like negative J times the magnitude of the current squared divided by omega C. So for capacitors, once again, we don't have any real part of complex power at all, which means capacitors only contribute to reactive power. But here, we always have a negative sign out front. So that means that capacitors are only capable of supplying reactive power. So that is specifically why on the utility grid, when we introduce temporary energy storage in order to help particular systems ride out the possibility of a blackout, so near like large scale manufacturing installations and stuff like that, we use what's called static VAR capacitor banks, because these guys literally supply reactive power into the system in order to regulate the voltage so that a blackout or brownout doesn't occur. Okay. We're going to talk a little bit more about adding capacitances into systems in a few minutes when we talk about power factor correction. But before we're able to do that, let's talk about what power factor itself means, because that's something that I've mentioned a few times to this point. We call the angle of the complex power the power factor angle, so it's probably a good idea to know what power factor is. So power factor is a measure of the efficiency, and I'm putting efficiency in quotes here because I don't mean efficiency exactly the way that we probably think about it, where efficiency would be a measure of, power out over power in or something like that in an electrical system. This is a different way to think about efficiency effectively, specifically related to a sinusoidally excited system. So power factor is a measure of the efficiency of a sinusoidally excited system. So mathematically, our power factor, which I'm just going to use a symbol of PF for power factor, is the ratio of the average power P divided by the apparent power magnitude of S. If we look at our relationships from yesterday, this is literally as simple as the cosine of our power factor angle theta S. So what our power factor tells us is how close to having a purely resistive system we have. I think I may have interrupted somebody. All right, so let's talk about why power factor is so important, particularly in the context of the electric utility grid. Okay. So average power, P, is literally what consumers, that doesn't look like consumers, pay for. So when you get your electric utility bill, it is literally just the average power that you have consumed multiplied by the amount of time in the month, effectively. Okay. So average power is what we as a consumer pays for. Apparent power is what the utility pays to generate. So effectively, if this ratio isn't very close to 1, the utility is wasting money. Well, what would make this ratio be not very close to 1? That is the presence of large reactive loads. So effectively, think about it in this context, okay? The electric utility pays to generate complex power that has some real part that gets converted into mechanical energy or turned into heat. And it also has to pay to generate reactive power, where reactive power is power that is absorbed by the load for one half cycle and then supplied back to the load for the second half cycle. And that happens over and over and over again. But it still costs them money in the form of potentially burning coal to power their steam turbines and stuff like that, or buying enough radioactive isotopes to fuel their nuclear reactor, even paying for the size of the copper wires or aluminum wires more nowadays that connect the electric utility grid together. The more current that's flowing on those lines, the more, the larger the conductors need to be, and the more money it costs the utility. All of those things right there are related to the reactive power. So in our homes, the overwhelming majority of the loads that we deal with are reactive. So if we think about our televisions and computers and stuff like that, all of those are resistive loads. Our lights are resistive loads. If we have heaters and things like that, if they are electric based, meaning that they don't burn gas or natural gas or anything like that, they are also resistive loads. It's only things like ceiling fans and maybe like our washer, things that effectively rotate in our homes, contribute to any reactive power that's absorbed by our house. Okay. So as a home consumer, this is not something that we are ever really going to have to pay attention to, because the overwhelming majority of our loads are purely resistive. So for the most part, we just absorb average power, so the utility doesn't really have to bother with us. But at a large scale manufacturing plant, where you might have several induction motors and things like that being used to power conveyor belts, large air moving fans, compressors in multiple HVAC units, things like that, you tend to have a larger inductive load on those systems, which causes those manufacturing plants to operate at a lower power factor, and that is expensive for the electric utility to maintain, and they pass that cost off to the manufacturing plant in the form of fines. Okay, so here in several minutes, we're going to talk about what large-scale manufacturing plants and stuff like that do to offset those costs, and it's a concept called power factor correction. But before we do that, I want to dig in a little bit more on this concept of power factor. Okay. Before I get into the nitty-gritty, does anybody have any questions?
I have a question. Under the complex power for the capacitor, is the magnitude of the voltage still supposed to be squared?
Yes, it is. Thank you for that, Leah.
Okay, thank you.
Thank you so much. I apologize for missing that. Any other questions? And sorry for ranting so long that you didn't get to ask your question until 5 minutes after my mistake. Okay, so let's talk briefly about the relationship between power factor and power factor angle. Okay, so knowing the power factor tells us information about the angle and vice versa. Okay, so let's start by looking at what happens when theta s is equal to, let's say, negative 90 degrees. So what would our power factor be if theta s were negative 90 degrees?
0.
It would be 0. So when theta s is negative 90 degrees, our power factor is 0. So we are operating at effectively 0% efficiency, meaning all of the electrical energy that is being generated by the utility is being sent back to them. So they are not able to charge anybody for literally anything. Well, this only happens when our load, and I'm just going to call this a generic load impedance, ZL, is purely capacitive. Okay. So what do we know about a purely capacitive load? Well, in a purely capacitive load, the current always leads the voltage, right? So when, let me draw it this way. Let's see. So when negative 90 degrees is less than theta s is less than 0 degrees, then our power factor, let me actually rewrite this, is going to be somewhere between. So 0 will be less than our power factor will be less than 1. And we can say that this is a leading power factor. This situation occurs specifically when ZL is called capacitive, but not purely capacitive. So that means that R is greater than 0, and X, our reactance, is negative or less than 0. Let me actually adjust this thing up here and say R is exactly 0 and X is negative. Okay. So if we know that we have a power factor of 0.73 leading, that tells us that our power factor angle is somewhere between negative 90 degrees and 0 degrees. And it also tells us that whatever load we have has real resistance and negative reactance. So that's what I'm talking about. Knowing the power factor or knowing the angle tells us information about the load. Okay. When theta s is exactly equal to 0 degrees, our power factor is 1. We commonly refer to this as unity power factor, and this occurs when ZL is purely resistive. So that means R would be, greater than 0, and X would be exactly 0. When 0 degrees is less than theta s is less than positive 90 degrees, our power factor will be between 0 and 1 again, but this time we call it a lagging power factor. And it's a lagging power factor because the current is always lagging the voltage. Well, the current lags the voltage in an inductive load. So we can say that ZL is inductive, where R is greater than 0 and X is also greater than 0. And then lastly, when theta s is exactly equal to positive 90 degrees, we once again have a 0 power factor where our load is purely inductive. R is 0 and X is greater than 0. Okay. So knowing our power factor or knowing our power factor angle tells us a whole lot about what's going on in our system. Tells us whether or not our voltage and currents are in phase or out of phase, what type of load we have, whether it's purely resistive, purely capacitive, purely inductive, or just a combination of resistance and inductance, or a combination of resistance and capacitance. So knowing the power factor of a system or a device tells a power engineer an awful lot of information about that particular device. Okay, before we jump back into in-class assignment 23, do any of you guys have any questions?
Dr. Harmon.
Yes, Austin, how may I help you?
Oh, what is that X standing for?
So back when we, great question. Back when we introduced the concept of impedance, impedance expressed in rectangular form consists of a real part, the resistance, and an imaginary part, the reactance. That imaginary reactance has a symbol of X.
Okay.
Yeah, so when I say ZL is purely inductive, that means that we know for an inductor, just as a quick aside here, I'll erase this in a minute. J omega L is the impedance. That's what we said. But when we looked at it in a more formal rectangular form, we called it 0 plus J omega L. The 0 here is the resistance, and this omega L here is the reactance. The positive sign tells us that X is always greater than 0. So it's literally just framing the stuff that we already knew in a little bit different way.
Okay, gotcha. Thank you.
No problem. I fully understand we have covered a ridiculous amount of material in this class, so do not hesitate to ask about stuff because it's rather easy to forget some of the stuff. Okay. Any other questions?
Yes, sir, Dr. Hartman. Just to tie into that last statement about the amount of material, you had mentioned somebody asked this question, I want to say back in like maybe class 1, about a formula sheet for exams. You mentioned that we do get one for this final exam.
So whenever I give this test in person, I allow the students to have a formula sheet for this particular exam, and I provide that formula sheet. Now, gosh, I don't know that I have it on this particular computer, but I will definitely get it on this computer prior to Monday's class meeting, and I'll need to find it to upload it to Canvas. This is a problem with having, I think, literally 4 different computers, 2 in my home office and 2 in my work office, and I'm not sure which one has the file that I'm looking for, so I apologize for that. So the short answer is yes, I do intend to still allow you guys to use an equation sheet. Now, I will say that the equation sheet that the students are given was not generated by me. I don't remember whether or not it contains any errors. I think it might have like one small error or something like that, not anything super big. And but this is where I'm probably going to sound like an ass. I genuinely don't think the equation sheet is necessary, so I'm still going to allow you guys to use it, but I am not going to waste my time fixing it, if that makes any sense. Yeah, so that's where I'm at on the equation sheet. I will happily allow you guys to use it, but you get to use it as is. Now, I am mildly concerned about the logistics of said equation sheet for an online exam. So I think what I want you guys to do is at the beginning of your test, hold up the equation sheet to show that it's the equation sheet that you were given, and then go from there. I just want to make sure that you're not using one that you generated. And I'll just have to kind of trust that that's all that you guys have, because I don't think I have time to watch 40 some odd videos of you guys taking tests before grades are due. Did that answer your question at all, or did I just rant?
Yes, sir. It does.
Okay. Any other questions? Okay, let's look at in-class assignment number 23, problem 2. So we worked number 1 the other day, so let's take a look at problem 2. So in this particular problem, we are asked to compute the complex power in polar form drawn by a particular load if we know certain things about said load. So let's look at part A really quickly here, okay? So in part A, we are told that our load draws 100 watts, okay? So if I tell you that a load draws 100 watts, what part of the complex power did I just give you?
The real part?
The real part, exactly right. So we could say that P, our average power, is 100 watts. Then I tell you that the power factor is 0.75 lagging. So PF is equal to 0.75 lagging. These are the only two pieces of information that you know about this particular load. I'm expecting you now to be able to tell me what the complex power is, okay? So because we literally just learned about power factor here within the last 10 to 15 minutes, I'll go ahead and effectively tell you what to do for this, okay? So recall that power factor is defined as the ratio of average power to apparent power, and it is also the cosine of our power factor angle. What we are trying to find is our complex power, which is simply our apparent power with an angle of our power factor angle. So we can use these power factor relationships and just reorganize things a little bit, right? So the apparent power is nothing more than average power divided by the power factor. And our power factor angle, theta s, is nothing more than the inverse cosine of our power factor. Does that make sense based on these relationships over here?
Yes, sir.
Okay, so let's plug in some numbers here really quickly, right? So we have 100 watts divided by 0.75, and then we have an angle of the inverse cosine of that same 0.75. Okay, so if I put that into my calculator, I believe I get 133.3, but let me double check that. Yep. So 133.3 repeating with an angle of 41.4096. So let's call that 41.410 degrees. And the units on this, because we are talking about complex power now, should be volt amperes. So my question to you guys is the sign on that power factor angle correct? Let me provide you some context for that question, okay? When your calculator performs the inverse cosine or the arc cosine operation, it will always return a positive angle, okay? It literally can't give you a negative angle. So we need to pay attention to the sign of that angle to make sure that it's correct. So how do I know whether or not that angle is correct? Or the sign on that angle is correct?
Lagging?
Exactly right. So because we were told that our power factor is lagging, that tells us that our angle is supposed to be positive. If we were told that our power factor was leading, we would actually have to force the angle to be negative because of the way that our calculators work, which I do by just putting a negative sign in front of the inverse cosine operation. But that is something that we need to pay attention to. So I wanted to bring it to your attention now. Anybody have any questions about what we did here for part A? All right, so let's move along to part B. So in part B, we are told that our load draws a current of I as an RMS phasor is equal to 9 plus J5 amps. So we have I is equal to 9 plus J5 amps RMS. When it is connected to a voltage, so this is an RMS phasor voltage, I can tell that because it has units of RMS, of 120 angle 32 degrees. Volts RMS. Using these two pieces of information, how would I compute the complex power absorbed by the load?
We would just find the
Reading.
conjugate of the current and multiply by voltage.
Exactly right. So that would look like 120 angle 32 degrees volts RMS. So the voltage gets left alone. How do we take the complex conjugate of this current? It's in rectangular form.
Change the sign of the imaginary part.
Exactly right. So what would that look like, Austin?
9 minus J5.
Perfect. So 9 minus J5 amps RMS. And then we'll just throw this in our calculator. So 120 angle 32, 9 minus 5i. And I get 1,235.476 with an angle of 2.9453. So let's call it 2.945 degrees volt amperes. Okay. So this one was just literally use the fundamental definition of complex power. Before we do part C, anybody have any questions about part B? All right, so part C, we are told that the load draws 1,000 watts. So what piece of information did I just give you with 1,000 watts?
The real part.
All right, so we know that our average power is 1,000 watts. And then we're told that it draws 100 VAR at a leading power factor. So what did I just give you there?
The reactive part.
Okay.
And
So-
the sign.
And the sign, absolutely right. So should this be Q is equal to 100 or Q is equal to negative 100?
Negative.
Negative 100 because of the leading power factor. Great job. So how would we get our complex power? Excuse me, and this shouldn't be watts, it should be VAR.
Do we just add these two?
Yeah, P plus JQ. So that's going to look like 1,000 minus J100 volt amperes. And because we want it in polar form, because that's what the problem told us, 1,000 minus 100 I is equal to 1,004 plus 988 with an angle of negative 5.7105. So let's call that 711 degrees volt amperes. It was literally that simple. And I hope it seems simple to you guys. Any questions on part C? All right. Part D, we're told that the load draws 450 volt amperes. So what piece of information did I just give you there?
Complex power?
So do you see a phase angle anywhere? So this is a
No.
little tricky, right? So because there isn't a phase angle, I would actually interpret that as the apparent power. So for part D here, I believe that I just gave you an apparent power of 450 volt amperes. And then our power factor is 0.65 lagging. Should have made it lead, but oh well. So using these two pieces of information, how would we get our complex power? So I literally just circled what we're looking for, right? So complex power in polar form is the apparent power angle, the power factor angle. So do we need to do literally anything to find our apparent power?
No, sir.
No, it was given to us, right? So we are going to have S is equal to 450. How do we find our angle?
You just do the inverse cosine of the power factor.
Exactly right. So the inverse cosine of 0.65. And so this is going to come out to be 450 with an angle of inverse cosine of 0.65 is 49.458 degrees. What should the sign on that angle be?
Positive.
Positive. Why?
Lagging.
Exactly right. 100%. Great job. All right. Does anybody have any questions on part D here? So effectively, in this problem, I asked you every way I could think of to make you solve for complex power. Okay. So let's look at part 3, and we're probably only going to do 1 or 2 parts of this just for time's sake, because I do still need to cover the power factor correction material. So in this particular problem, you are given, and this should have a tilde over it because it's an RMS voltage. So you're given an RMS phasor source voltage as well as 3 impedances, and you're asked to determine the average power absorbed by impedance ZA, apparent power absorbed by ZB, reactive power absorbed by ZC, and the power factor at which the source supplies power. So let's work on parts B and D. Okay, and I'll leave A and C for you guys to do. So how I would approach any problem dealing with complex power or the parts of complex power, so average power, reactive power, apparent power, etc., would be to figure out how to solve for the complex power and then just take the information that I need from that, okay? So since we're focusing on just parts B and D, let's identify the pieces of information that we would need to determine those quantities, okay? So I think for us to determine the complex power absorbed by impedance ZB, we need to know either the RMS phasor voltage drop across element ZB or the RMS phasor current flowing through element ZB. We only need to know one or the other. Technically, we could use both, but if we want to answer this question in the most efficient way possible, we're going to wind up using one of these two alternative relationships that I circled here because it only requires us to know either the voltage or the current when we know the impedance. For us to determine the reactive power, excuse me, the power factor at which our source is supplying power, what we're going to need to know is the current leaving the positive polarity terminal of our voltage source. So those are the two things that we're trying to find, okay? Something about either the voltage or the current across impedance ZB, and then the current leaving the positive polarity terminal of the voltage source. So who can tell me a way to get either the voltage drop across ZB or the current flowing through IB?
Voltage division.
So voltage division, to me, is the easiest way to get that information. If, for whatever reason, you were so inclined to try to find the current, though, you could do a source transformation on this guy and then use current division to find IB first. Not saying we have to do that by any stretch of the imagination because it is technically two steps where we can get the voltage in one, but that is definitely a way that I've seen students approach this one, so I just wanted to mention it. So using voltage division, we could say that VB is just our source voltage times. So notice that impedance ZB is in parallel with impedance ZC, and that voltage VB is the drop over those two impedances in parallel. So I'm going to write this as ZB times ZC over ZB plus ZC. And in my denominator, I will have ZA plus, and then that same parallel combination from above. ZB, ZC over ZB plus ZC. So I'm going to throw this into my calculator really quickly, and I typically do this by just storing all of the impedances. So 2 angle 15 is stored as A. 10 minus 5I, I'm going to store that as B. 8 plus 6I, store that as C. And then we have 120 angle 45 times B times C over B plus C all over A plus B times C over B plus C. And when I solved for that voltage here, I got 90.8961 with an angle of 43.082 degrees. Volts RMS. So using that piece of information, I could solve for the complex power absorbed by impedance ZB by simply taking the magnitude of VB and dividing it by ZB conjugate. Oh, sorry, the magnitude of VB squared and dividing it by ZB conjugate. So what's the magnitude of VB?
$90.896.
90.896 volts RMS squared. So if ZB is 10 minus J5, what is ZB conjugate?
10 plus J5.
10 plus J5, absolutely right. So putting this in my calculator, 90.896 quantity squared divided by, oops, I missed a zero there. 10 plus 5i. I got 738.983 with an angle of negative 26.565 degrees volt ampere in polar form, and 660.967 minus J 330.483 degrees volt ampere, sorry, no degrees there, volt amperes in rectangular form. So since we are trying to find the apparent power, which of those four numbers is the apparent power?
Magnitude on the polar.
Exactly right. So the magnitude of our complex power, which is our apparent power, would be 738.983 volt amperes. Looks like I have a little bit of rounding error, not surprising, but pretty close to what we would expect. All right, so determining power factor. So I mentioned that we would need to find this current, which is one way to solve for the power factor, but I also mentioned previously that the power factor angle is also the angle of the impedance. So we actually have two options here. Sorry, I didn't mention this earlier. We can find this current, or we can literally just find ZEQ and then take the cosine of the angle of ZEQ. Which way would you guys prefer?
The easier one.
Which one's easier? I argue that they're both pretty easy. So, like, I think that we could find IVS by applying Kirchhoff's current law at this node, right? So the current flowing in is IVS, and the current flowing out is VB, which we already know divided by ZB, plus VB divided by ZC. So that, to me, seems pretty simple. finding the equivalent impedance is also pretty simple. So I need you guys to tell me which way we're going.
Let's do Kirchhoff's current law,
Okay,
since we already know VB.
sounds groovy. So for part D here, we could say that IVS is equal to VB over ZB plus VB over ZC, right? So that's literally just this current flowing down plus this current flowing down. So can we all agree with that based on Kirchhoff's current law? Nobody's saying it's wrong because it isn't, so I'm going to keep on trucking. So we could actually make this a little bit easier. So that would be VB multiplied by 1 over ZB plus 1 over ZC, so that I can do slightly less work. So I'm going to go ahead and just put it in my calculator that way, since I already have VB in there. So I have VB stored in my calculator as X. So that's going to look like X times 1 over B plus 1 over C. And I got a current of 14.6565. So let's call that 657 with an angle of 35.957 degrees. Amps RMS. From this, the complex power supplied by my voltage source is the source voltage, which is 120 angle 45, times the complex conjugate of my current, which is going to be 14.657 with an angle of negative 35.957 degrees. Sorry, amps RMS. And so let's see, 120 angle 45 multiplied by the conjugate of my prior answer gives me 1,758.787 angle 9.043 degrees. And since I'm finding volt amperes, and since I'm finding power factor, I'm going to leave it like this because this is my personal preferred form. So having the complex power supplied by my source, how would I determine my power factor?
Cosine of the angle, and the sine of the, whether it's be lagging or leading, is based on the sine of that angle.
All right, so cosine of 9.043 degrees. So cosine of the polar angle of my prior answer comes out to be 0.98757. So let's call that 988. And is this power factor leading or lagging based on the sine of the angle?
It's lagging because it's positive.
Exactly right. Any questions on what we did here? So just to reiterate things really quickly here, all of the circuit analysis that we have done previously in the frequency domain, that is literally all that we're doing now. We're just using RMS phasor voltages and currents. So this last section of the class on all these power relationships didn't introduce any new circuit analysis whatsoever. We're just taking the circuit analysis that we already know how to do and using it to put numbers into equations. Okay, so I know that the amount of material that I've given you guys can definitely be overwhelming. I do not deny that at all. I'm just trying to help you think about it for what it is. This last bit is just plug and chug and figuring out which equation you need to use. So I'm trying to make that as easy as possible. Okay, so we've got 32 minutes left, so I'm going to talk about power factor correction. And I'm going to have to do this kind of quickly, but we've already laid down a pretty darn good framework. Okay. So let's say that we have an inductive load whose power triangle looks something like this. So here's our real axis, here's our imaginary axis, and then here is our complex power S. And I'm going to call this S old because it represents the complex power prior to power factor correction. Okay. And then this angle right here is going to be theta old. Okay. Well, the projection of S old onto the real axis is going to be P old, and the projection of S onto the imaginary axis is going to be Q old. Okay, so we haven't really done anything new yet. So if I want to improve the power factor at which my load operates, do I need to make that angle theta old larger or smaller?
Smaller?
Smaller, right. Because the closer we can get that angle to 0 degrees means the closer we are to operating at a power factor of 1. Okay, so I need to make that angle smaller. So in order to do that, what I need to do is effectively inject or add something into my system that is going to supply VARs. Okay, so I need to supply VARs because I'm trying to make Q smaller. So think about it in this terms. So maybe this would be my result after power factor correction, right? So we'll call this S new. The projection of S new onto the real axis is still P old. The reason we don't want to change P old is because that would effectively be changing our utility bill, right? So technically speaking, we could correct the power factor by making P larger, but that's just going to cost us more money by running up our electric utility bill. So the way that it makes the most sense is to reduce Q. So we would now have this guy over here, Q new. Okay. So how are we going to supply VARs to our system?
We use it in a system with more inductance.
So let's look back up here when we were figuring out what things did, okay? So adding resistance causes P to get larger because we're absorbing more average power. So that would do it, but it's a wildly stupid way to do it because that would run up our utility bill. Adding inductance would actually make Q larger because inductors absorb reactive power. So by process of elimination, and also because it literally says it right here, we need to actually add capacitance into our system to offset the amount of VARs that our inductance is absorbing. Okay, so we correct the power factor in a system by adding capacitance. And it's typically added in parallel so that we don't lower the amount of voltage that our load is seeing. Okay. So if this particular diagram corresponded to a system like this, where we have some source voltage Vs supplying power to an inductive motor, we would literally correct the power factor by placing some capacitance C in parallel with our voltage source. Realistically, we could place the capacitor C in parallel with our motor, and in the way that I've drawn it, they represent the same things, but power factor is usually corrected at the source because our transmission lines usually have some amount of inductance as well. So drawing this as a more realistic representation, we might have some transmission line impedance ZW is equal to R plus JX. So placing our capacitor in parallel with the source corrects not only the power factor problems caused by the inductive motor, but also any inductance contributed by our transmission lines as well. Okay. So let's talk about what's going on with the math here effectively. Okay. So S old is simply P old plus JQ old, and S new is equal to P old plus JQ new. So the complex power that is being provided by our capacitance, let's call that S cap, is simply S new minus S old, which looks like P old plus JQ new, minus P old plus JQ old. The P olds cancel each other out. So that's going to look like J Q new minus Q old, or J times Q capacitance. Okay. So this is what's going on in the system, and that's what's causing our graph to look the way that we want it to. Now we need to figure out how this relates to our capacitor value itself. And the short answer is that this bit right here is the complex power absorbed by a capacitor. This equation right here is also the complex power absorbed by a capacitor. That's why there's a negative sign out front. And so we're just going to put those two things equal to each other and then solve for C. Okay. So if we set this equal to negative J times the magnitude of the voltage squared times omega C and rearrange, what we find is that the capacitance C is equal to negative Q cap over the magnitude of the voltage drop across the capacitor squared times omega. But sometimes finding Q cap can be a little bit annoying. So I actually prefer this relationship. Okay. So P old times the tangent of theta old minus the tangent of theta new divided by the magnitude of the voltage across the capacitor squared times omega. This is what tells us how to size a capacitor based on our old power factor, which is related to theta old, and our desired power factor, which is related to theta new. So let's put this equation into use by looking at in-class assignment 24, problem 1. Okay. So we are told that when connected to a 120 volt RMS 60 hertz power line, a load absorbs 4 kilowatts at a power factor of 0.8 lagging. And we're trying to find the value of the capacitance to place in parallel with a load in order to increase its power factor to 0.95. So let's remind ourselves of our equation. C is equal to P old times the tangent of theta old minus the tangent of theta new divided by the magnitude of the voltage drop across the capacitor squared times omega. And now let's figure out which pieces of information do we have, right? So do we know what P old is?
Four kilowatts.
Exactly right. Because kilowatts is telling us average power. So 4 kilowatts, okay? Do we know theta old?
It's not the cosine of the power factor. It's cosine inverse of the power factor.
Exactly right. So that would be the inverse cosine of our old power factor. So that would be the inverse cosine of 0.8, which I believe is 36.87 degrees, but let me double check that. Absolutely, 36.87 degrees. And should that be angle be positive or negative?
Positive lagging.
Exactly right. Thank you for that. Do we know theta new?
It's the cosine inverse of 0.95.
Exactly right. So because we know our target power factor or our new power factor, we can solve for that as well. So inverse cosine of PF new, which is just the inverse cosine of 0.95. I got 18.195 degrees. Do we know the magnitude of the voltage drop across the capacitor?
$120 volts.
120 volts RMS, absolutely. And lastly, do we know the angular frequency that the system is being excited at?
$120 pi radians per second.
You're 100% correct, Joey. How did you get that, please?
Just the, I guess the normal frequency times 2 pi.
Exactly right. So the linear frequency in hertz times 2 pi gives us our angular frequency, omega 2 pi f, which is 2 pi times 60 hertz, or 120 pi radians per second. Great job. And so now we literally have all of the pieces of information that go into solving for that capacitor C. So we would just plug numbers in, and I'd be willing to bet that we get 310.439 microfarad. This problem, I hope, seems pretty easy, and it is pretty dang close to the type of questions that I usually ask on your exams. Okay, so let's look at problem 2. Actually, before we move on, does anybody have any questions about this particular problem? Okay. So let's look at problem 2, and then we will wrap up for the day. Okay. So in this problem, we have a 230 volt RMS source at 50 hertz source is used to power a single phase induction motor that has an impedance of 25 plus J10 ohms. And we are asked what value of capacitor should be placed in parallel with the motor to raise its power factor to 1. Okay. So once again, our equation is C is equal to P old times the tangent of theta old minus the tangent of theta new divided by the magnitude of the voltage drop across the capacitor squared times omega. Okay. So for this particular problem, there is not a power mentioned at all. So we're probably going to have to do some work to figure out what P old is. Okay. Anybody have any thoughts on what that might look like? And it's okay if you don't.
You take the voltage squared over the impedance.
So it won't be the voltage squared over the impedance. It's the voltage squared over the conjugate of the impedance.
Conjugate of the impedance.
So S for our motor is just the magnitude of the voltage drop across our motor squared, sorry, that should be a tilde, divided by the conjugate of our motor's impedance. So what's the magnitude of the voltage drop across our motor?
230 volts RMS.
Thank you. And what's the conjugate of our motor's impedance?
25 minus J10.
Okay. So I'm going to throw that into my calculator. Stop hitting the wrong buttons, that would be great. So I get 1,964.657 with an angle of 21.8014, so let's call that just 801 degrees. Volt amperes in polar form, and in rectangular form, I get 1,824.138 with an angle of 700, sorry, that's not right, plus J, 729.655 volt amperes. All right, so we now have information about what is effectively S old, okay? So what's P old?
1964.657.
I disagree, because that is the apparent power, and we're looking for P, which is the average power.
Would that be 1,824?
The real part of the
Exactly right. The real part of the rectangular form, 1824.138. What's theta old based on the information that we have?
21.8.
Exactly right. So the angle that the motor is absorbing power at is theta old, because the motor is our load prior to power factor correction. So literally just that angle, 100%. What's theta new going to be?
Zero.
Exactly right. So it's going to be the inverse cosine of our new power factor. And our new power factor happens to be 1. So that's literally just going to come out to 0 degrees. What is the magnitude of the voltage drop across our capacitor? So we're told that we are placing it in parallel with the motor.
It's the same as our VRMF, right?
Yeah, it's the exact same thing as the voltage drop across the motor, which was 230 volts RMS. And then lastly, what is omega going to be for this?
a 100 pi radians per second.
Exactly right. So with a linear frequency of 50 hertz, which is what's commonly used in Europe, we would have an angular frequency of 2 pi times 50 hertz, or 100 pi radians per second. And we would simply plug all of this information into our one equation, and I would be flabbergasted if we didn't get 43.905 microfarads. Okay, before we wrap up for today, just want to remind you all that I finally got around to placing all of the practice tests and stuff like that on Canvas. I again apologize for taking so long to get that done. I will be working on the exam throughout the course of the weekend, so I'll have my laptop with my email client pulled up and all that kind of stuff. So if anybody has any questions, please do not hesitate to ask anything of me. Clarification of material, what's going to be on the test, all that kind of stuff. Anything is fair game. I just want to make you guys feel as confident and comfortable as possible going into this exam. Does anybody have any questions for this afternoon before we knock off, and then, you know, all that kind of good stuff? All right. Well, I hope you guys have a great weekend. Legitimately, don't study too hard. Take some time to enjoy yourself. Your mental health and all that kind of stuff is important. But study as much as you feel is appropriate. And I will see you guys on Monday for the review session. Thank you for your time.
Dr. Hartman.
Yes, Austin, how may I help you?
For 23, I submitted what the work we had from previous, but do you want us to, I don't know if you need to extend the submission for what we've done today?
No, I'm not going to worry about it.
Okay.
So submitting what you had is perfectly reasonable. Again, they're not graded for completeness or correctness, really, even though we're working most of them here in class. They are literally just to get you to think about what it is that we're doing. So I'm perfectly acceptable with you turning in a partially completed one because we only completed a part of it before class wrapped up on Wednesday.
Yes, sir.
So if we saved it until we finished it, was that not the thing to do?
It's perfectly fine if you did. So let me go on to Canvas really quickly and extend the due date or whatever, just in case you didn't turn it in, because I certainly don't want anybody getting penalized for misunderstanding the instructions. So
All right, thank you.
let me do that really quickly, because I definitely don't want anybody getting shortchanged for not turning it in when I specifically said we were going to finish it up today. That's
Dr. Hartman.
Yes.
So I just wanted to make sure real quick. So for our 3 exam grades, we just take our lowest exam grade and make it 15%.
Exactly right.
Is it a non-zero or it does not matter?
Doesn't matter. So are you effectively asking if my grade is good enough and I'm fine with not making an A, can I skip exam 3? The answer is sure. It's your grade.
Okay. Yes, sir. I was just making sure, just going into it.
Yeah. Shoot me an email just so that I can double check everything. But I mean, the math is on the syllabus. I'm sure you're right. I just don't want to tell you skip the test if you're satisfied with this grade and then come back and be like, oh man, you should have taken it. So
Okay. Yes, sir.
just to cover both of our asses, let's
Yes, sir.
No, for what it's worth, I've been in a similar situation, except that Dr. DeRosa just kept telling me to take the damn test. So I wound up with on 112 in his statistical mechanics course. Not to brag or whatever, but I guess kind of to brag because I'm an arrogant douche.
No, it's all good. All right. Well, I'll email you.
Yeah. Sorry, I'm having a brain fart as to how to edit the due date of this, but I think I have it sorted out. So let's do today at 2. So let's make it due tomorrow at 2. All right. So anyone who was unable to turn in class assignment number 23, or who chose not to turn it in, should be able to do so now, just to make sure that they get credit. And I apologize for the confusion there.
All right, thank you.
No problem. Any other questions before I close the Zoom call?
Dr. Hartman, I just had a sort of a general question about complex power. I probably should have asked it on that day of class, but basically the reactive part of the complex power, is that just like power with respect to the angle? Is that all it is?
So the reactive power, I'm not entirely sure that I understand your question being power with respect to the angle, but the reactive power represents what's going on with temporary energy storage effectively. So it's associated only with inductances and capacitances. Inductors absorb reactive power and capacitors supply reactive power. So whenever we're trying to do what's called voltage regulation on the utility grid, which is making sure that the voltage never dips below a certain threshold, which could cause damage to electrical machinery and stuff like that, we actually have to make sure that we place capacitor banks near those systems so that the voltage never drops down too low and shuts things down. So like think about that in the context of a manufacturing company like Texas Instruments over in Dallas. They actually have their own dedicated static VAR network. So it's just a huge capacitor bank to make sure that their system never goes down. So they have generators and all of that kind of stuff, but they have to be able to ride that dip in voltage when an event causes the power grid to go out and their generators to kick on. And the reason why their voltage can literally never change is because if their ability to manufacture chips like even goes down for 30 seconds. It takes hours, if not days, to get all of that machinery back up and running. And so it would cost them millions of dollars in business.
Yeah, that makes sense. I'm just wondering, with so like what the kind of machines they're running, it's like they're taking more power from the chain, like the alternating of the current, not just the magnitude of it. Is that a better way of asking it?
Sorry, ask that again.
So it's kind of like you were talking about how most devices we use are resistive, but the ones that are reactive sort of it's like it corresponds more to the angle of the wave, not the magnitude of it. Am I thinking of that correctly, or is it still more different? Because I understand the math, that's not really the hard part, but I'm still trying to wrap my head around it.
So, I mean, they are drawing they're drawing a large amount of power in general. So, I mean, they have large resistive loads and all of that kind of stuff. So, like, I'm talking about this in the context of, and this is something that we didn't really talk about in this class because we always just kind of assumed that a voltage source was able to provide current. But like a practical voltage source, there is a limitation to the amount of current that it can provide. And that is true for both DC sources and AC sources. So in an AC network, it is the reactive power that provides the energy storage that makes sure that the voltage being supplied by the source never falls too low.
Okay, that makes more sense. It's
So it's a context of like a voltage source can only supply so much energy. And sometimes we need to give it a little bit of help because if the current draw is too high, the voltage has to fall in order to supply more current.
that definitely makes sense. Okay. Thanks.
No problem. Any other questions? All right. Well, I know I said it a couple of minutes ago, but I hope you guys have a great weekend. Realistically, do not study too hard. You know, study as much as you feel is appropriate, but take some time for yourself this weekend and enjoy it. Because here in the next 2 to 3 weeks, we're going to be starting this whole train all over of just classes all the damn time. So anyway, thank you guys for your time, and I will see you for the review session on Monday.